Good morning. Our topic of discussion is motor position. Group members are Aparna Ajay, Aswani K, Aswin Abraham, Dany and Harish K P. I am Dany and let's start the presentation. The courtesy of tutorial is given in this slide. Modeling of system. DC motors that use feedback controls are called DC servo motors. They have precise angular position and have quick response. This presentation will focus on modeling and position control of DC motors. The common actuator in control system is a DC motor. It directly provides rotary motion and when coupled with wheels or drums or cables can provide translational motion. The electric equivalent circuit of armature and free body diagram of the rotor are shown in the following figure. In general, we know the torque produced by the DC motor is proportional to current. T is equal to Ki into I, and also bike EMF is proportional to angular velocity. So these two equations are used. We know that both bike EMF constant and motor torque constant is equal. So we use K to represent both. So by using Newton's second law and Kirchhoff's voltage law, these two modeling equations are derived. Transfer function. We know that transfer function is a Laplace transform of output to Laplace transform of input. Its ratio. So from the modeling equation, we take Laplace transform on both sides, and by suitable calculations, we obtain the transfer function. By using MATLAB software, we made out the continuous time transfer function. This is the command, and we obtain the transfer function, and we use the notation P motor for that. We also need state space equation for modeling. So we choose motor position, motor speed and armature current as state variables. Again, armature voltage is treated as the input and the rotational position is chosen as output. So by using this command, we get state space equation, and the result is given in the left side. So for the modeling purpose, these are the values used. These are the values of physical parameters. Conditions for desired system to be modeled are settling time should be less than 40 milliseconds, overshoot less than 16%, and there should be no steady state error. So this have to be taken in concern while we modeling. First, we take the open loop response. In the MATLAB, we write these commands, and we can see the step response is increasing. So that we can say the output is not bounded. So this system is stable, and also you can see is stable command is used. It gives the output logical 0. This states that the system is unstable. In closed loop, we give a feedback using feedback command. Step response is obtained, and also maximum peak overshoot and settling time is also calculated and obtained. From the step response, we can see that, and also from the values of maximum peak overshoot and settling time, we can see that steady state error appears to be 0, and also overshoot is less than 16%, which is our requirement, but settle time requirement is PID controller. A PID controller continuously calculates the error value, that is the difference between the desired set point and measured process variable, and it applies a correction based on proportional, integral and derivative terms. So Kp is the proportional gain, Ki is the integral gain, and Kd is the derivative gain. So P, I and D are the corrections given by PID controls, and the equation in the next slide, you can see the input to the plant is U, and the equation is given here, U of t, and also the transfer function of the PID control is given below. The general effects of each control parameters are given in the next slide.
Proportional controller is mainly used for reducing the steady state error of the system. We have done proportional controller for different proportional gain Kp to see different in closed loop step response. MATLAB program for step response correspond to different values of Kp are given below. From this plot, it's clear that there is no steady state error at the time of step reference, but it has a significant steady state error when a disturbance is added. To have zero steady state error in the presence of a disturbance, we need the disturbance response to decay to zero. The larger the value of Kp, the smaller the steady state error, but it never reaches to zero. And also increasing larger values of Kp has the adverse effect of increasing the overshoot and settling time. So adding an integral term will eliminate the steady state error, and derivative term can reduce the overshoot and settling. We designed a proportional integral controller to get rid of the steady state error due to the disturbance. We will set the value of Kp as 21 and test integral gain Ki ranging from 100 to 500. From this graph, it's clear that for the response to the step reference, all of the responses look similar. The amount of oscillation increasing slightly as Ki is made larger. The response due to the disturbance changes significantly as the integral gain Ki is changed. The larger the value of Ki employed, the faster the error decays to zero. So, we will set the value of Ki as 500. But the response to the reference has a longer settling time and more overshoot. To reduce the settling time and overshoot, adding a derivative term to the controller. Proportional derivative controller is mainly used for reduce the settling time and overshoot. We will set the value of Kp as 21 and Ki as 500 and test derivative gain for the different values of Kd 0.05, 0.15 and 0.25. When Kd is equal to 0.15, we can meet our design requirement. So after the design of PID controller, we get the time domain specifications as follows. We see that the response to a step reference has a settling time of roughly 34 milliseconds. That is, it's less than 40 milliseconds. Then overshoot of 12% and there is no steady state error. Additionally, the step disturbance response also has no steady state error. So when we use a PID controller with a Kp equal to 21, Ki equal to 500 and Kd equal to 0.15, all of our requirements will be satisfied.
Root locus control design. The main idea of root locus design is to predict the closed loop response from the root locus plot, which depicts possible closed loop pole locations and is drawn from this open loop transfer function. Then by adding zeros and or poles via the controller, the root locus can be modified in order to achieve a desired closed loop response. Given below is an open loop transfer function and the root locus is plotted. The poles that are obtained are 1 into 10 raised to 6, minus 1.4545 and minus 0.0001. Clearly, the pole 1 into 10 raised to 6 is very huge and is located farther to the left in the complex plane. In such scenario, we can perform a model reduction. So if you have a transfer function which is one or more poles much farther to the left in the complex plane than the other poles, the effect on the dynamic response can be hidden by the very slow, more dominant poles. The poles obtained after model reduction are 0 and minus 59.2260. But this does not fulfill the criteria of overshoot being less than 60%, settling time being less than 40 milliseconds, and no steady state error. This is where we use an integral controller. To remove the steady state error due to a constant disturbance, add an integrator in the controller. But then the system becomes no more stable. Therefore, we use a PI controller. Using PI instead of I control adds a 0 to the open loop system. Place the 0 at s is equal to minus 20. Thus, we achieve a stable system with zero steady state error. Settling time will be high though, but we need it less than 40 milliseconds. Therefore, we use a PID controller. To reduce settling time, add two PID zeros at s is equal to minus 60 and s is equal to minus 70. Closed loop poles can be placed within both the settling time and percent overshoot requirements. As you can see, we've obtained a 0 at minus 60 and a pole at minus 59.2. The third closed loop pole moves from the open loop pole at s is equal to minus 59.2 to the open loop 0 at s is equal to minus 60. Thus, we can cancel both these by using the minrail command. In order to obtain the gain corresponding to a point on the root locus, we can use the rlogfind command. This will ensure that the response will be nearly as fast as possible with minimal overshoot. Given below are the response to a step reference with PID control and the response to a step disturbance with PID control. As you can see, the overshoot is given as 13.6, which is less than 60%. There is no steady state error, and the settling time is given as 3.86 milliseconds. Therefore, all of the design requirements have been met.
Frequency domain method of controller design. The frequency domain method of controller design is generally analyzed by plotting body plots. So the main idea of the frequency based design is to use the body plot of the open loop transfer function to estimate the closed loop responses. Adding a controller to the system changes the open loop body plot, thereby changing the closed loop responses. The open loop planned is unity feedback does not satisfy the given system requirements. So we can say that the system does not get any system requirements. So to attain the system requirements, we add different compensators. So initially we add an integrator by doing it in MATLAB. So we can get a body plot and a step responses of that integrator. By that step response, we can see that by the time s tends to infinity, there will not a particular value of the amplitude, so it tends to infinity. So by that step response, it can be said that it is unstable. Next, the gain and phase margin specification and control design. Here the measurements are given in time domain analysis, so we convert it into frequency domain. So that overshoot of the step response gives the phase margin and bandwidth gives the settling time. And the results demonstrate that we have decided to have at least 50 degree of phase margin in the attempt that meet the overshoot requirement, and also a closed loop band of 250 radian per second is decided to additionally to achieve the settling time requirements. And to get that desired frequency domain specification, we add zeros at zeros s is equal to minus 60 to the compensator, and check the body plot and step response from the program equation. We will get the pole and 0 of the lead compensator by this, and adding the lead compensator to the system, we get body plots. After analyzing the plot, we can say that the phase margin is about 250 rad per second, but the gain is too small, so we give additional 600 decibel gain to the system. By that, we get a plot of phase margin 49.8 degrees in the gain phase margin, and gain crossover frequency is 236 radian per second, which are close to our goals of 50 degree and 250 rad per second. From the step response, it can be seen that the overshoot is too large and the settling time is better than dash better. In order to reduce overshoot, we will adjust the lead compensator to provide more phase margin. Then we will get a 70 degree of additional phase of 250 rad per second, and gain of 315 gives us phase margin of 70 degree and the overshoot less than 60 degree. from the step response it is clear that the overshoot is fine, but the settling time is too long. So again a gain of 670 added to the requirements. At last we get less than 16% overshoot and settling time less than 40 milliseconds. So our we meet our design requirements. Next is DC motor position by the simulating modeling. Here the system will be modeled by the summing the torques acting on the rotor inertia and integrating the rotor's angular acceleration to give the velocity and integrating the velocity to get the position. Also Kirchhoff laws will be applied to the armature. Here the input is given as the voltage and output is taken as the position, and terms between these are collectively taken as the subsystem. When comes to controller design, in the open loop responses, that the input is given as the step response and output as scope, and setting the step time at 0, we get an appropriate unit at the step at t is equal to 0, and also sets the stop times as 0.2 seconds, and by this we will get the graph. And due to some errors we don't receive any more output from simulating in our work related to the motor position. We model the system using PID controls, root locus control, frequency domain method and simulating. So thank you.